point architecture was originally based on 8087 coprocessor, and this was a very slow design. It had 80-bit extended precision registers that used a push down stack. If you studied push down automata, you'll know what a push down stack is, and it was very, very slow. So we came up with faster floating point instructions. So as I was speaking yesterday, fast math is there, which you can use at the cost of precision, which will give you a speed up if you are ready to sacrifice some precision in exchange. So the real game changer came up when Streaming SIMD extension 2 SSE2 came out. So that allowed 4 into 128-bit registers. So basically, it added 124 of 128-bit registers that could be used to do two 64-bit double precision multiplications or four 32-bit double precision multiplications. And these are known as SIMD registers. It stands for single instruction and multiple data. Basically, you have only one input data and one instruction, which is your vector add or vector multiply or vector divide or vector subtract, and you are operating on multiple pieces of data together. So, for example, here you have matrix multiplication, good old matrix multiplication, right? DGEM. So you have DGEM over here, which is int n double a double b double c. You're just multiplying normally. Now you look at the assembly instruction here. You have move SD, which loads one element of C into XMM register. XMM is a data register. Then you have vmove SD, which loads one element of B into XMM1 register. Then vmul SD, which again it's doing one operation at a time. So now what you can do is you can optimize this code. Okay. So uh, you can optimize this code by using certain special intrinsics. So the C programming language and C++ programming language, they provide something known as intrinsics, which are like special functions that you can declare with a double underscore. So here you have hash include x86 intrin.h. This is actually a header that you can call. And if you use underscore underscore m256d, that will tell, or here underscore underscore mm256 load pd, these tell the compiler that you have to use a vector instruction instead of a scalar instruction. So the opposite of vector is scalar here. So over here, this will generate your vector instructions. So instead of this, it will add your vmulpd here, which is loop parallel multiplication of four numbers at once. Vmove apd will do parallel addition of four numbers at once. And so basically, this below program, just by adding these special intrinsics, runs about four times faster than the above program. Of course, you might have never seen C programs that look like this, because we try one basic principle that we follow is we try to make sure that all of this happens automatically. We don't want users to be stuck writing parallel code, right? We don't want them to struggle through with figuring out how to parallelize their code, so they try to do it automatically. So one way that we can also speed up operations is by doing an operation known as strength reduction, which means it's an optimization where you try to replace a more costly optimization, such as multiplication or division, by a cheaper optimization like shift left or shift right. So shifting left will give you multiplication by 2, and shifting right will give you division by 2 for unsigned numbers. So why is floating point accuracy important? Again, for a lot of scientific code, there are bugs where which can have catastrophic consequences. So basically, you have to realize that bits have no inherent meaning. You can have negative representation just by choosing that, okay, I'm choosing to represent the farthermost bit by as one, and the leftmost bit by zero is positive and one is negative. It's up to you, and you need to account for this. So instruction set architectures support arithmetic, signed and unsigned, and the MIPS ISA has a few core instructions. So here, one thing worth noting is that again, even though the x86 instruction set has like thousands, more than 1,000 instructions, very few of them actually get used, right? Less than 100 of them get used, and probably the most frequently used ones are 20 or 30 of them. Okay. So now coming back to the processor design, right? So we are talking about hazards and pipelining and forwarding the other day, right? So uh, basically, you can get more better pipelining in a few ways. Like you want faster pipeline, you want your processor's performance to increase, right? So you can do that in a few ways. You have to like you have a few choices. One is that you can deepen your pipeline. Like you can split this pipeline into more stages. So, for example, you want to you have four stages over here. You have an instruction fetch and instruction decode and like an ALU, a data access, and a reg. Like five steps are there. One, two, three, four, five. So you can split this into 8 or 10 steps, and then you can layer them together so that each step takes lesser time, and you get speed up that way. But that comes at the cost of hardware complexity and the possibility of stalls increasing. You can also take care of certain hazards by trying to do branch prediction, right? You can do branch prediction, you can do forwarding. So, branch prediction is basically you try to predict if a branch will be taken or not, so if a loop will exit or not. So, the main thing is that in superscalar processors, that means processors that execute more than one instruction per clock cycle, right? So you have processes that have an IPC of CPI of more than one. So when the cycle for instruction is sorry, when the cycles per instruction is less than one, then you end up with something known as a superscalar processor. And a superscalar processor is something that is executing more than one instruction in one clock cycle, and you have multiple cores, like you have 4 cores, 8 cores, 16 cores, and all of these cores might be running parts of the program, right? So suddenly waiting for the loop to execute so that condition to fulfill so that you can go check what is happening next is something that's going to take a very big penalty. Like the performance penalty is too big. So instead, what you do is you start predicting the outcome of branches. Okay, you do branch prediction. So you can do this in a few ways. You can either use static branch prediction or you can use dynamic branch prediction. So static branch prediction is you just like try to estimate based on how the code looks, right? If it has like a condition that starts at one and ends at 1,000, then statically you can analyze and do this. A dynamic branch prediction is when you actually measure the behavior and you try to figure out from there. So dynamic branch prediction basically means that you have to start from uh, running the program, and then you see how the program is running, and the next time it runs the processor makes certain assumptions. So the processor can do things like preload some data into the cache, store some of the data in the main memory. It will know that which branches are taken. This is why often it happens that the first time you run a program it's slower, and then when you rerun the program it sort of runs faster because your dynamic branch prediction and your system has stored the state, right? So basically, pipelining can improve the performance. So we have moved from instruction level parallelism, here subword. The earlier level parallelism that we were seeing was parallelism at the instruction level with vector instructions. Now we're going to parallelism through the hardware, right? So this improves performance by increasing instruction throughput, like executing multiple instructions in parallel. This is not parallelism within the instructions itself, it's parallelism through how you're running the instructions. And there are subject to hazards like anything else. So finally, you have pipeline registers. So these blue lines that you see here are pipeline registers because you need them to forward data at the end of every round. So if you don't forward the data that you computed in the previous cycle, then you'll end up with stalls again. So we saw a single clock pipeline earlier, right? So this is how those pipelines work. So when you have like an instruction fetch, which is the first step, you have like this part in blue that's highlighted being used. So mainly the program counter. Then you have the data memory being accessed or the instruction memory being accessed. Finally, when execution happens, the ALU is active. And then finally, when the memory access happens, the data memory is accessed, and then the write back happens in which the data is written back from the memory to the registers. So all of these steps happen one after the other. They happen in parallel in case of superscalar processors. So one way to like sort of get speed ups over this also, that okay, we have a pipeline, we have this, and we want to speed it up even more. So one few things that you have to avoid in that is hazards. So for example, you have this sequence here where you are subtracting the value of register 1 from register 3 and putting it in register 2. And then you have an AND operation between register 2 and 5 and you're storing it in 12. Then you have OR. So you have to look forward for these dependencies and detect them. So for this, there's formulas like Bernstein's formulas and all that tell you when to forward, when not to forward, and it's a whole field of analysis. Even your compiler has to avoid these data dependencies and race conditions, right? So it's a complicated field of study which involves like a lot of data path analysis on figuring out how to avoid these kind of stalls. Your compiler can to negate it to some extent by reordering the instructions, but it cannot prevent all the stalls. So if it stalls, basically you have a no-op, which means an instruction that does nothing except for allowing the clock to tick so that the later parts of the pipeline can catch up to the earlier parts of the pipeline. That's what this bubble represents here, right? So these no-ops are inserted and that's how you deal with it. So stalls are obviously going to reduce your performance, but you do need them to get correct results. The compiler can rearrange code, but you have to know the data about the pipeline structure. Basically, a compiler has to be aware of the hardware, but that's not always the case. So you can here it shows you some examples of avoiding branches by reordering code or by assuming that the branch was taken or not taken. Dynamic branch prediction becomes more important in deeper and superscalar pipelines. So here you can either have some kind of a buffer which stores the results of the previous run, like what happened previously. It stores those kind of details, and it's indexed by like recent branch instructions. You have a table, or you have something like a 1-bit predictor which kind of tries to predict whether like it stores the previous value and it goes based on that. 2-bit predictor is like if there are two wrong predictions, it will, like, the problem with 1-bit predictor is, like, let's say that your loop is, I mean, you have some statement that is going every alternate iteration or something. So it's true once, it's false once, and then it's true again. So the 1-bit predictor exits too early for that. So you have 2-bit predictors which give you a second chance. If it's wrong twice, then it will exit out. So even with the predictor, we still need to calculate the target address, and there is a 1 cycle penalty for that. So the branch target buffer can cache this address so that you can have the address ready. There are also interrupts that happen. Basically, when you are trying to predict something, right, it might be that there might be an unexpected change in events that, like you might lose power, the kernel might panic, the program that you are running might segfault. So all of these things are the exceptions, right? So these exceptions have to be dealt with. So if you have exceptions, then you have to do a lot of things. You have to read the cause, like you have to figure out why the exception happened. Then you have to store the state of the program. Like your CPU will be currently running something, so you have to store that state, right? And then you have to take care of the interrupt, execute whatever the interrupt requires you to execute. For example, if it's a loss of power, then you have to save some data that's in the registers in the memory before it's lost forever in that 200 millisecond gap before the power goes off. If the kernel panics, then again you have to store some data so that your system doesn't end up in a corrupted state. If it's seg faults, you have to bail out. So you have to run those instructions and then you have to try to come back to running whatever you are running, right? So simplest approach is like if you can have multiple exceptions also. For example, a kernel panic and a seg fault might come together. So there are approaches where you sort of daisy chain the different interrupts together to sort of deal with them, or you just deal with them as they come. Sometimes there's an importance table, right, that works, that defines like which interrupts are more important and which are less important. Anyway, so coming back to ILP, so instruction level parallelism, right? So to exit before this, we'll take a deeper look at subword level parallelism. So subword level parallelism is basically defined by something known as parallelism at the instruction level. So it is the chief way that it's done is something known as vectorization. And now we'll take a look at vectorization in LLVM, right, which is one of the compilers that implements this vectorization. So basically, we try to do something called auto-vectorization, which means that instead of that 256 mul PD, whatever stuff you saw, where you have specific intrinsics, we try to do that automatically. Basically, you write regular C code or C++ code or Python code or Fortran code, and underneath the compiler and the processor together take care of making the program vectorize. So, so let's go for this. So, auto vectorization is basically the art of detecting instruction level parallelism and to make use of SIMD registers, which is vectors to do parallel computation. So here is one example of scalar addition. So scalar addition, you have 5, 6, 7, 8, 1, 2, 3, 4, and they're being added one by one, cycle 2, cycle 3, cycle 4. So in cycle 1, you add 5 with 1. In cycle 2, you add 6 with 2. In cycle 3, you add 7 with 3. Cycle 4, you have 8 with 4. So this is like adding four element arrays. So you need 4 cycles to do 4 additions. In vector addition of the array, you do all of them together. So you 4 times as fast, right? So what is auto-vectorization? Basically, it can be done in any language, but some languages are more expressive than others. And a lot of like heavily performance-oriented code today, C++ code today is in fact I mean, a lot of performance oriented code is written in C++ and Fortran and some of it in C. And these are the languages that implement vectorization the most. So again, like here's an example from a few different programming languages on how you have sequence of repeated instructions. So it can that repeated instruction can be a for loop. So you have one dot dot n. This was an older notation that GCC supported. I think it's not supported anymore, but you could declare loops like this, and then you can also have a for loop that looks like this or a for loop that looks like this. So all of these are basically representing the same thing, but how do you vectorize this? So where did it all come from? So up until 2012, we had only Poly. So Poly was the polyhead. Poly is one of the projects in the LLVM project. It still exists, and it used polyhedral analysis, which is it's a very mathematical field of study, something that uses Pressburger formulas and polyhedral representations to do certain optimizations. And it had basic support for vectorization. There were no cost tables. So I'll come to what a cost table is soon. Basically, a cost table is a series of calculations that tells you whether you should do an optimization or not, right? So you have the concept of a cost table where you have to basically decide, like, should I carry on this so there are few things that you have to decide before deciding to vectorize. One is the legality, like, am I allowed to do this optimization or not? Like, basically, if there are two arrays that you are trying to add, and the dimensions of the arrays are not compatible, then vectorization is not legal there. You cannot do that, right? But if it is legal, then the second thing is you have to do judge is it profitable? Like, basically, okay, fine, I can add these two arrays, but does it make sense to vectorize or not? So sometimes vectorization may not be faster than a scalar equivalent, right? So these cost tables and all that didn't exist. So in 2012, we introduced something known as the BV vectorizer, which is a basic block vectorizer. I think I covered basic blocks in the last session. So this was optimizing at the basic block level. There were no loops. It was very aggressive. You could create too many shuffles, and it got better over time, mainly because of the heuristics improving. So in October 2012, the loop vectorizer was introduced. So it could vectorize a few of GCC's example. It was split into legality and vectorization steps. Legality is checking again if it's legal or not. There's no cost information, single block loops only. So if you have a for loop inside a for loop, it's not going to mm, like work. So basically, we realized that, this kind of one size fits all vectorization is not a good idea. We got to, like, figure out some heuristics, right? We have to figure out some way to tune this thing for different processes, and also we created something known as the cost model. So then we split vectorization into three steps. Okay. One is legalization. Can I do the vectorization or not? Cost is whether it is worth it. And then finally the vectorization, which is creating a new loop, vectorize the loop, ditch the older loop. So basically the compiler is rewriting your code. And one very cool thing is that till now it was the compiler doing this, but C++26 is adding support for something known as reflections, and it's so reflections allow you to like, basically do this where you can write a program that will inspect its own structure and generate new code based on that information during compilation. So even compilers are gaining this kind of reflection feature. And I mean, programming languages, compilers already had it. Compilers already worked on the principle of, like, doing this, but now we have this kind of reflection being added to programming languages as well. So we generated cost tables for ARM and then PowerPC. A lot of costs and features were added, and there were a lot of benchmarking done for ARM x86 PowerPC. And even within x86, the cost tables, which give you the trade-offs between doing various kinds of vectorization or not, they're different for Intel and AMD, and they're different for different processors. So there's a lot of this stuff involved. It should work for all targets. So this reduced a lot of regressions as in cases where earlier the compiler was successfully able to do vectorization, but now the compiler is unable to do vectorization, and it enabled the vectorizer to run at lower optimization levels. So one thing with optimization levels is from O1 to O3 and O4 and beyond, it progressively causes code bloat because the vectorizer might, like, do introduce vector instructions. It may unroll the loops. It may inline functions. It can do other things. And again, the more aggressive optimization levels are meant to represent more risky optimizations that the compiler is doing. For example, O4 combines FLTO and FFastMath into the optimization pipeline. So I think there is a way in Clang where you can do print before all and print after all. So if you do print before all and print after all with your compiler flags, you can see all of the passes and all of the flags that were executed. So generally at O1 level, you only perform the optimizations that you are very sure are very safe. So now many of these vectorizers are so safe, as in they rarely make a mistake that causes the program itself to crash, so that you can run it at lower levels. So the basic block vectorizer that I spoke about that was introduced earlier, that still exists. This basic block vectorizer that is there, that still exists, and even that began to benefit. The real amazing stuff started happening around 2013 when something known as the SLP vectorizer came out. So SLP stands for the superword level parallelism. So it follows the same principle as our basic block vectorizer. The basic block vectorizer again does vectorization only at the basic block level, where it just takes blocks and it does not like do individual statements. So SLP vectorizer follows the same principle, but it's bottom up. Okay, it's faster to compile because it deals with blocks instead of individual lines of code. It has fewer regressions, more speedups. It operates on multiple basic blocks like trees, diamonds, cycles. So diamonds, as in, I think you can understand what a diamond is. It's just a closed graph, right? Like one second, I'll just open up Paint here because I think that's the easiest way to explain. So, a diamond is basically you have like one statement here where there are two loops on either side, and then both of them converge to one ending statement, right? So, you just have like this one statement that branches out into two, and then both of them converge towards the same conclusion or the program ending. This is like a diamond, and then you already know what a tree looks like, right? So you have cycles. So some of these graphs can be directed. So like this might be a loop. Like you have cycles in the graph, like they all point towards each other. So you can start from one end and end up in the same end, like because there are self-referential loops and stuff. So it can take care of all of these kind of things, and like there are some very interesting algorithms that are hidden inside that deal with these cycles and all. For example, so in coverage also you have to count uh, this. So let me. So even in code coverage, you have to count loops and loops inside this thing. So there is this Havik and James cycle detection algorithm. So this is basically it can count all of the cycles in a graph. So the compiler actually does implement these sort of algorithms internally, right, to detect these graphs. So, but it does not vectorize function calls. So there are two vectorizers that are operating in parallel. The SLP vectorizer works at the block level and the loop vectorizer works at the loop level. So now they're enabled by default in OS, O2 and O3. So OZ is size paranoid, so it will mostly disable it. And so we have tried the loop and SLP vectorizer. It's existed for a long time. There's now even I think another. Let me see, pause vectorization if there's any resources on that. So, so branch on superword condition code vectorization is there. So this particular type of vectorization was invented at AMD. So like this is another type of vectorization. So multiple types of them are there. Yeah. So what do we have today basically? So currently we can deal with a few things. So we can deal with loops with unknown trip count. So the trip count in a loop is simply the number of times the loop runs, right? Each run of a loop is a trip. So we can deal with loops that have unknown trip counts by using some heuristics. We have reductions where basically reduction is something like sum over array. You're taking a very big array and you're like adding up everything into the first element, or you're adding it into a variable. So you're basically summing over the array. We can handle if conversions, reverse iterators. We can even do vectorization of mixed types where we have a basic block level vectorization mixed in with a loop vectorization. And of course, we can do vectorization of function calls when that is there. So we have runtime checks on pointers, we have inductions, uh, we have scatter gather instructions, and we have partial unrolling of loops also. So, so we have these functions inside LLVM can vectorize instructions which check strides. So the loop stride is basically how much the loop jumps. So basically, if it is I plus plus, the stride is 1. If it is I plus 4, like basically the loop is incrementing by 4 every instruction, then the stride of the loop is 4, right? So there's a function to check, and then can vectorize memory to check for load and stores. If we can do parallel loads and parallel stores, there are vector load and vector store also. So there's a function for that also. So right now we need to check if the target supports SIMD or not. So like basically, does it have single instruction, multiple data type? This thing. We have to detect what register is there and how many rows are there. So basically, if you have 128-bit registers, you can add 16 8-bit numbers or 8 16-bit numbers or 4 32-bit numbers. So we have to figure out, right? Your compiler might run on ARM, it might run on x86, and it might run on PowerPC or RISC-V, and each of them will have a different width, right? The width of the registers will be different. So the number of lanes will be different. So the like basically how many lanes does your processor have? Your processor might support like 4 cores, 8 cores. It might have support simultaneous multi-threading. So based on the number of lanes, it will differ. Then you have tail call optimization where you optimize the last call, which is the tail call, and you have to do the cost analysis. So there's also unroll factor, which is basically you can unroll the loop by a factor of some unroll factor, which can be like either a number that you hard code. So for programs that you write, you can actually put pragmas and stuff. And pragmas are again something that we'll talk about shortly. So basically, these are examples of auto-vectorization, right? This is vectorization that's done by the compiler. But if you want to like manually do this kind of vectorization, or you want to manually make sure that your compiler can do these operations, you need to use OpenMP. Okay, so OpenMP is basically a tool, or not a tool exactly. It's like a language that's built on top of C and C++ that allows you to use pragmas. So it's an extension of the language. So you can like put a hash omp.h, and while compiling, you can use fopenmp, and you can compile the program. So one interesting thing is like these pragmas are statements that are normally ignored by the compiler unless the compiler is specifically asked to like look at them. So because all of the pragma syntax starts with hash, so if you write an OpenMP program and run it on a regular computer, it will, or on a regular compiler which does not support OpenMP, the program will still run. It will just not run parallelly. So, like for example, you could do an experiment. You can write a program to compute the Fibonacci series, not the recursive version, the iterative version, and you can try for a very large value of n, like say 10,000. So even on your laptop, that will take a few seconds to run, possibly 20, 15, 20 seconds to run. So you can use hash pragma OMP parallel by including this omp.h, and like you can use this hash pragma feature, like hash pragma omp.h, and then either in GCC or in Clang you can use -f openmp. Both support that same this thing. So it will basically execute it on all of the threads that are available on your system. But so your this thing, your program will run 8 times or 16 times faster. So instead of like your Fibonacci program taking 30 seconds to run, it will take only 2 seconds to run. However, the problem is that if you don't take care of which parts of your program are single threaded, so you will end up with problems. Like you will get the Fibonacci series, but it will be out of order. It will not be in order. So to take care of that, you have to worry about critical sections and deadlocks and all of that, which you might have studied in operating systems, right? So OpenMP is all about threads, and there's a lot of threads. Basically, the number of threads is the number of processors in your lab system. So, if your phone has four cores, it has four threads. But of course, AMD has SMT, which is simultaneous multi-threading, which Intel calls hyper-threading. So I think till like the 11th gen or 12th gen, Intel also supported like two threads per core. But with some of the newer Intel laptops that are there that have this P-core, E-core hybrid infrastructure where there are power cores and efficiency cores, basically they have turned off hyper-threading. I don't know for what reason. So for those Intel processors, again the number of course is equal to the number of threads. So OpenMP allows you to create duplicate copies of the program internally and run them in parallel. And there is one master thread that controls the synchronization of all of these. So this is also an example of parallelism, but it is explicit parallelism. It is parallelism through statements that you are giving in the program. So it does not mean that OpenMP is not popular. OpenMP is very popular, and a lot of very fast code that is written in the world, everything from quantum chemistry to thermodynamics to n-body physics simulations, all of them use OpenMP. But the only problem is that you have to do it by hand. You have to worry about deadlocks, race conditions, and how the code is executing, if the master thread is controlling the threads properly or not. It's not automatic. You have to worry about it. Whereas for automatic vectorization that we were discussing in LLVM, there are it's automatic. So there are many other tools like OpenMP. There's Intel Silk Suite CALK, which also does the same thing. But OpenMP is the most popular one. So that is an example of handwritten like parallelism, and this is automatic parallelism. So right. So in the present, again coming back to auto-vectorization, for each basic block in the loop, we can widen the instructions, basically use vector instructions instead of scalar instructions, handle multiple load stores together, and if it's supported or not supported, we can go over it, right? We can also handle fee nodes, and so where do we intend to go with this? Uh, so LLVM is coming up with some interesting things. So for example, LLVM vplan is literally stands for the vectorization plan. So LLVM is creating something called a vplan architecture. So this is something that's very new, and the idea is that currently we have multiple vectorizers, and these vectorizers don't deal with some stuff such as outer loops. So outer loops, as in like when you do matrix multiplication, for example, if you're doing matrix multiplication for 2D matrices, there is a loop, and then there's a loop, and then there's a third loop inside the other two loops, for, right? So the outermost loop is very difficult to vectorize. So these kind, and the LLVM vectorizer, at the end of the day, it's very conservative. Like if there is a case where even there's like a 1 in a million chance that the program will crash due to vectorization, the LLVM vectorizer will refuse to vectorize the code. Sometimes it might even be that to you it is obvious that the code should be vectorizable, but because your code has pointers and the compiler is unable to alias the pointers or chase the pointers, it will refuse to vectorize the code. So LLVM is coming up with something called the vectorization plan, which is an explicit model for describing vectorization candidates. It serves as both optimizing candidates, including is estimating their cost, and also for their final transition into IR. So it's currently used to drive code generation in loop vectorize. So in LLVM, there's a file called loopvectorize.cpp. So that does use this pipeline. So they're trying to build all this where you have an initial vectorization plan, and then you check the legality, then you check the remarks, and then you finally adjust based on that. So you can go through it. It's a very interesting thing that they've come up with, and Poly is still an independent project, and far as I know, Poly is somewhat of a dead end. And of course, we also have pragmas. So these are not OpenMP pragmas. There are general pragmas in Clang also. So here the problem is that different programming languages like C and C++ and different compilers, LLVM and GCC, might have slightly different pragmas. So recently, at least for the last 10 or so years, LLVM and GCC have been trying to collaborate to make sure that the pragmas that they have, these are these compiler hints, that they have the same syntax. So if LLVM implements a pragma called pragma clang loop vectorize, then GCC will make sure that at least it supports the same syntax. Even if the general syntax is different, they will make sure that it supports it. So now, fortunately, we are reaching a state where you can give statements like hash pragma vectorize with 4 unroll 2, which means vectorize with a width of 4, unroll factor of 2, as in unroll this loop twice, and the width is 4, as in the trip count, the stride is multiplied into this thing. So we are still working on this. So there are a lot of interesting pragmas. There's a pragma called IVDEP, which is used for vectorization. There's a pragma for unrolling. There's a pragma for inlining. There are the negative version of these pragmas also, where you can say pragma no unroll, pragma no inline, which will not inline and not unroll. So the LLVM vectorizer still does not support a non-unit stride support, basically where the stride is changing. So like you have A plus S, A plus 2S. So here your stride is not like an even number like 1 or 2 or something. So LLVM can't support this. So they're working on it. So this is like some example of like subword level parallelism and instruction level parallelism. So again, coming back to ILP, we have superscalar processors, right? So basically, modern day processors have to get a ton of speed. Now, how do you get that speed? So you have to do a few things, you have to basically you exploit ILP. So I'll cover ILP from this slide. I think. Let me load it up. Until it loads up, I'll just come back here. So okay. I hope my internet didn't go and I'm still connected to the call. Can okay. Yes, go. Yeah, yeah, yeah. Yeah. So let me come back here. So it's okay. We can use this only. So basically, you have to execute instructions one after the other, and even if you have like subword level parallelism with vector instructions, still you can have performance issues, right? So superscalar processors are all about going beyond that initial CPI of one. It's by going like trying to execute more than one instruction per clock cycle. So superscalar processes where you saw that instruction fetch, instruction decode cycle over here, right? In these chapters. So you can do a few things. So to increase the ILP, you can either deepen the pipeline, which means like if you have instruction fetch, instruction decode, execute, write back, and all those 4 5 steps, you can deepen the pipeline so that you have lesser work per stage, or you can duplicate the pipeline. So you have multiple of these pipelines working, multiple pipeline stages working together. So you have CPI of less than one, so we use IP. So see, so there is something called multiple issue. So static multiple issue, where basically you have a process, like the diagram is given over here. You have instruction fetch, and then you have a decoder, and then instead of execute, you have a dispatch queue. Okay, and this dispatch queue will package your instructions together, and it will there's something known as a reservation station. So your compiler will basically package certain instructions together, and it will send these packages parallelly across multiple execution steps. And then finally there's a reorder or completion buffer which will put those steps back in order, complete it, and then stop. So this basically instruction fetch is still linear and instruction decoding is still linear, but after that it's parallelized out. So it's an example of SIMD. So reservation station again, it decouples decoding and execution, and it checks for hazards also, the hazards that we discussed yesterday. So there are multiple designs for the reservation station also. So it can either be like one or split into four, and 4 or 5. So modern day processors all have like all of this reorder buffers and this thing to sort of like do multiple instructions in parallel. So one very important thing here, concept that comes in is register reusing and register renaming. So you have to remember that even modern day processors have something like only 32 or 64 registers. And if each of those registers are like 4 bytes, you still have like what, maybe a few kilobytes of memory or a few bytes of memory in the register, right? So your registers can store very little data. So you have to figure out how to reuse those registers as much as possible. So one common question that comes up in this is like, okay, using the least possible instruction registers, how do you execute these sequence of steps, right? So let's come back to this now. So static multiple issue, which is basically compiler groups instructions to be issued together. It packages them into instruction issue slots, and the compiler detects and avoids hazards. So this is the origin of VLIW, which is the very long instruction word format. So here the compiler can do things like combining uh, even 120 word, 20 instructions or 30 instructions all into one very long instruction and then executing it together. Compiler will pick instructions that execute sequentially as possible and don't conflict or don't cross branches. Then there is dynamic multiple issue, which is not done by the compiler, but it's done by the CPU. So the CPU examines these instructions and chooses instructions to issue on each cycle. The compiler can help, it can reorder the instructions from its end, but basically the dynamic multiple issue is run by the processor, not by the compiler. So one of the things that comes in over here is speculation, right? And speculation is also one of the good things that we have in modern day processors that gives us performance. And unfortunately, it's also got side effects. So to increase performance, basically all modern day processors have realized that you have to guess what to do with an instruction. So like they either make a guess that this loop will be taken and they start executing the instructions after the loop also, or if they guess that it will not be taken, they bail out and they execute whatever was not there in the loop. So problem with this is that you can end up executing instructions that were never meant to be executed. And this speculative execution is the source of vulnerabilities like Spectre and Meltdown. So speculation can happen both at the compiler and hardware level, where compiler can reorder the instructions. It can move load up before branch. It can include some fix up instructions. It can include some fix instructions which will help you recover from incorrect guesses. So hardware can also look ahead for instructions to execute, and hardware is usually what does speculations. So now one big question is that we discussed exceptions very briefly, right? That exceptions can happen when exceptions happen, your processor has to stop the execution and then carry forward. What if the exception happens when the processor is executing something speculatively? So then you are in danger because you have to stop and you have to come back and you might figure out that you are wrong or not. So there are strategies for dealing with that. So you can either do dynamic speculation or static speculation. You can add support to deal with this. So again, we static multiple issue is what we discussed, issue packets. So this is something VLIW is something that's supported by x86 mainly, and it's how you end up with super long instructions. So VLIW is something that exemplifies the CISC architecture, the complex instruction set architecture, where you have multiple very long instructions combined together. So the main problem with scheduling static multiple issue is that again your compiler has to remove some or all of the hazards. It has to reorder the instructions into issue packets. It has to remove dependencies, and yeah, the compiler has to deal with all of the backends. And this is one of the reasons that writing the backend is so hard. You have to really know the in and out of your hardware before doing that. So there are MIPS processors with static dual issue, so which is like basically there are two cores, or like not exactly cores, as in there are two execution units that can execute in parallel. So here you can see that just like our earlier data paths, there are two ALUs instead of one ALU. So these are also there. So the more executions are happening in parallel, so there are more chances of hazards. Now, once we study the memory topic, and memory will be something that we cover on another day, you'll come up with all sorts of nonsense like what if the processor is writing an updated value to the cache of one core while some other core is using the same data, and its value of the L2 cache is something different. So now you have the same data which has one value in one side and some other value in somewhere else. So all of these kind of hazards come up once you have multiple parallel executions, right? So one of this is one of the optimizations that can take advantage of this kind of parallelism is unrolling, because if you unroll the loop, then you can execute both of those unrolled statements in parallel, and this is why unroll factors are often chosen to in powers of 2. So you will see unroll factor like 2, 4, 8, 16, because it neatly matches up with the number of cores and threads in the processor. Then you have dynamic multiple issue in superscalar processors, where the CPU decides whether you have to issue 0, 1, or 2 in each cycle. And then there's dynamic pipeline scheduling. So this is dynamic pipeline scheduling's idea is that the compiler has sent the instructions to the CPU in one order, but the CPU can still choose to execute those instructions out of order. But the thing is, it has to make sure that it writes the results to the registers in the right order. If it writes the results to the register in the wrong order, then again, you will end up with hazards. So again, this is the same diagram that we saw in those IIT Madras slides. It's the basic same idea. You have instruction fetch, instruction decode, multiple reservation stations, and then one final commit unit, right? So uh, again, these are things that we have covered. Register renaming, why it's important, because we have to use registers very efficiently. So does this work? I'm saying that there are so many ifs and bits conditions, right? Like it may stall, it may hazard, it might error out. Like, does it work? So yes, it does work, but it doesn't work as much as we'd like. So that's why after 2006, yes, we got dual core phones and quad core phones and 8 core laptops, but they're not 4 times as fast or 8 times as fast as the dual core version. One is because you have to write code to take advantage of parallelism. And as anyone will tell you, parallel programming is very hard. If you want to like have increase the challenge of anything that any code that you are writing, try to make it parallelized and it will become 10 times harder because suddenly you have to worry about all sorts of problems. So programs can have dependencies that limit ILP. Some dependencies can be hard to eliminate, like pointer aliasing. So if you are if you have one pointer that points to another pointer and then that points to another pointer, then your compiler will get lost and it will not be able to like do that much parallelism. So some parallelism is there, but it's hard to expose. And then there are problems with memory delay. So basically, the reason we have to do all of these hacks and all of this stuff is because the processor is much faster than the memory, right? The processor runs like your registers take like zero point 0.1 to zero point 0.2 nanoseconds to like register a value. Your the cache memory takes between 1 to 10 nanoseconds. Your main memory takes between 40 to 100 nanoseconds, and then your main disk, your RAM is even slower, which takes like a few microseconds, and then finally the hard disk or SSD is there, which takes millions of cycles. So basically, the whole field of computer organization or design is so complex because the processor is much faster than the memory that it's accessing. So this is like the crux of the subject. So here is like two modern day processors. Like by modern, I mean relatively modern. The Core i7 920 was Sandy Bridge, which came out in like 2010 or something. It was the first of the Bridge series processors, Sandy Bridge, Ivy Bridge, and so on. So uh, you can compare it to an ARM Cortex A8. So the the TDP of A8 is 2 watts, whereas for i7 it's like 130 watts. So i7 consumes a whole lot more power. The clock rate is 2.5 times. So the i7 supports floating point, whereas ARM does not. That doesn't mean it can't do floating point math. It just has to simulate it using the integer instructions. Both support multiple issue. Uh, so the peak IPC of i7 is 4, whereas for A8 it's 2. There are 14 pipeline stages in both of them. So we saw examples with 5, right? So instruction fetch, instruction decode, execute. This has 14. And A8 has in order scheduling, whereas i7 has a dynamic out of order scheduling. And they both have multiple levels of caches, L1, L2, L3, and there's also a branch predictor in both of them. So even with though A8 is like only a 2 watt or whatever processor, the performance is actually pretty good. So these are on spec CPU benchmarks, GCC, MCF, gzip2. So all of these spec benchmarks are taken from workloads that are like real world benchmarks, and they do pretty well. So if you want to see the organization of a real processor, it's something like this where you have 32-bit instrumented cache. There's a TLB, and what a TLB and what a cache is and what L1, L2, L3 is something we'll cover in the future. But yeah, so the design of the modern day processors is pretty complicated. So a few things to watch out is that pipelining is not easy. The devil is in the details, right? You have to design the processor very carefully, and even if you do pipelining, the hardware is only half of the story. The compiler still has to do a shit ton of things to make sure that it works correctly. And pipelining is an idea that's theoretically independent of technology. It doesn't depend on tech. the basic idea is simple, but implementing is hard, right? You have to take care of all of the things that may happen in the future. So, poor instruction set architecture design can make pipelining harder. Pipelining in x86 is very complicated because x86 has variable length instructions. Some instructions like jump have only like one jump instruction followed by an address, whereas on the other hand, VLIW instructions are like 120 instructions long. So it's very hard to pipeline, right? So in modern day processors, what we've done is at the front end of the processor, there is a CISC to RISC decoder, which basically takes x86 instructions and converts them into shorter micro ops, which more look like RISC instructions so that pipelining is easier. So yes, it's not CISC versus RISC, it's more like both are converging towards something each other. Then there are addressing modes that are very difficult. As we discussed addressing modes. Addressing mode is simple, but then you have register indirect mode and like auto increment and auto decrement modes and all sorts of things which make it complicated. And then branching is again something that's really complicated. So basically, the instruction set architecture design influences like data path and control. It also influences software in a way, and it influences what your compiler is able or not able to do. So there are other topics. So basically, in ILP also here we saw that there are like multiple ALU organizations where there are multiple ALUs and there are multiple hazards, right? So this is something that you have to try out. It's something that you can't understand easily. Maybe I'll give you guys a few questions that you can work through to really understand how hazards are and how hazards work. But I think that now is a good point to stop here because everything else that we cover after this will have to be covered only when we cover memory. So, memory is a topic that is as complicated as the processor that we covered till now.